Hi, the next one is Kendall's tau. The idea is similar to Spearman's rule. So when we have some outliers, we want to make a correlation coefficient which is robust against those outliers. But just the definition is different from rho. So Kendall's tau is a different version of correlation coefficient, which is invariant by monotone transformation, but not based on rank, but we have this quantity. So the number of observations which satisfies xi minus xj times yi minus yj is positive, minus the number of observations for xi minus xj times yi minus yj is negative. Then divide by the total number of combinations. So this is n combination 2, so the total number of pairs. So the idea is that if x and y are positively correlated, like this figure, the most lines have, increasing line. So if x coordinate is larger, y coordinate is also larger. So actually, these lines satisfy those conditions. Maybe I cannot write everything, but maybe some sections are missing. But the most observations, most pairs, it's increasing. X value is larger, then y value is also larger. So it satisfies this condition. Maybe some exceptions, such as this, or maybe this or this. But we have the fewer linear line segments with green. So if positive relationship overall, then this tau is positive and otherwise negative. And the total number of combinations, the total number of pairs is n times n minus 1 over 2. So everything satisfies the first condition, then tau is 1. If everything satisfies this second condition, then tau is negative 1. So still the tau is between a positive 1 and negative 1. Yeah, so this is the definition for tau. So if you use you calculate tau by hand, maybe it's faster than maybe Pearson's correlation coefficient, but if you use computer, it's much slower because we have to calculate the n times n minus 1 terms. So that's much slower than just taking, the summation of n terms as in Pearson's or Spearman's correlation. Yeah, so just an example here. So we have 5 observations. This is the same as the last time. Then we calculate the number of pairs which satisfies the first condition and satisfies the second condition. And actually for this one, the first condition is only satisfied for one pair, the 3, 8, and 6, 10. So 6 is larger than 3 and 10 is larger than 8. So this satisfies this condition, but all others do not satisfy. For example, this one, the 8 is larger than 3, but the 0 is smaller than 8. So the second pattern is that we have more the observations for the second condition. So the 1 and 9, so that is the 1 minus 9. Then in total, we have 10 pairs. So 10 is equal to 5 times 5 minus 1 over 2. So this is negative 0.8. So Kendall's tau is negative 0.8. So you can use the correlation function to calculate Kendall's tau. So you can just adjust the method. You can calculate everything, the Spearman, Pearson, Kendall by COR function. And Kendall's function is invariant by monotone transformation because basically we compare just the xi and xj and which is larger. So it's not numeric. Just we use the information on which observation is larger. So it's invariant by monotone transformation. It doesn't change rank, so it doesn't change Kendall's tau. And testing on tau is also based on simulation. So you can also use the COR dot function to test. Yep. So most of the time, we use the Pearson's correlation. So especially the two variable x and y are bivariate normal. So that is a kind of mound-shaped distribution on the xy plane. Then we use the Pearson's correlation, and we have if we have outliers or some irregular data, very skewed data, usually we use the Spearman's correlation. So, but most of the time we use Pearson, sometimes Spearman. And Kendall, I think they're pretty rare, but still that we can use it instead of Spearman's correlation.